Okay, so we know how to graph polynomials. The question now is how do we factor polynomials? So we will look at two theorems, the intermediate value theorem and the rational root theorem, and then two types of division, long division and synthetic division, and that will get us to factoring polynomials. So what are these two theorems? So intermediate value theorem, this tells us that if we have a polynomial, and this should be a capital if here, if 2 points have opposite signs, then this is x-intercept somewhere between x1 and x2. So here's a polynomial, and take our x value, we get our y value by plugging in x into the polynomial. If x is 1 and y is 2, what does that tell us? Well, if we plug in 1, we get 1 minus 1, which is 0 minus 2. So p of 1 is minus 2. If we plug in 2, we get 8 minus 2, which is 6, minus another 2, which is 4. So if we graphed our polynomial, what would that give us? Here's our x-axis, here's our y-axis. One point on the graph is x equals 1, y equals minus 2. And one point on the graph is x equals 2 and y equals 4. So the graph goes through these 2 points, but one is below the x-axis and one is above the x-axis. So what has to happen? Well, somewhere between 1 and 2, the graph has to cross the x-axis. So there's an x-intercept in there somewhere. We can call that a root, right? So somewhere between 1 and 2, there's a number that we can plug in that will give you 0 out for y. We don't know what that number is, but we know there has to be one. So how can we actually estimate the root of this? Well, we know that the root, once we draw this table, x, y, 1 minus 2, 2 and 4. So the root that we're after, whatever it is between 1 and 2. So question mark, whatever it is going to be 1 point, something, 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 right? Whatever the decimal is. So you can plug in other numbers and see what you get. If you plug in 1.5 and 1.6, you get that the y value is minus 0.125 and 0.496. So this point is below the x-axis because its y-coordinate is negative. This point is above. And if you go from below the x-axis to above the x-axis, somewhere in there you have to have an x-intercept. So we know that our unknown number starts out 1.5 and then something, something, something. And you can keep going, right? You can always just plug in more and more numbers, 1.52 and 1.53. If you plug those numbers in, this is about minus 0.008, and this is about 0.051. And so again, this is below, this is above, so we can say that our unknown root is 1.53 something, something, something. And you can keep going and going. And, computers can generate these kinds of approximations pretty quickly. And so when you actually ask a computer, what is the x-intercept, like GeoGebra, it'll give you a long decimal out to however many digits you want. So, but basically what we're doing there is we're saying, the x-axis is here. If I can find points above and below, I can work my way in to figure out what the x-coordinate is. And it doesn't have to be 0 necessarily, right? So suppose we have p of x equals 20, and we want to find that solution. And here we're still using the same function, p of x equals x cubed minus x minus 2. So x, y, we want to know, is there a solution somewhere in there? So 3 and 4, if we plug in x equals 3, you get 22. If you plug in x equals 4, you get 58. And 40 is between those two numbers, right? Between the two y values. So what we're saying here is, well, if you plug in 3, you'll get 22. But if you plug in 4, you get 58. Y equals to 20. I don't think I want y equals to 20. I want y equals to 40. So y equals to 40 is here. So our graph starts at 3, 22, goes up to 458, and somewhere through there, right, there's an x value that will give you y as 40. So that's an immediate value theorem, right? If you can figure out two y values, right, the graph has to go up from one to the other or down from the first to the second. So we can get some nice results here, right? One is that every odd degree polynomial has to have at least one x-intercept. And remember that the end behavior for odd polynomials is either like this or like this, depending on whether or not the leading term has either a positive coefficient or negative coefficient. So if you go down to minus infinity on one side and positive infinity on the other side, you got to go through the x-axis at least once. And you could go through it a bunch of times, of course. You could have a whole bunch of x-intercepts, but there's got to be at least one. So x to the 17th got to have some kind of x-intercept in there somewhere. So the rational root theorem is another theorem that helps us figure out where roots might be. And it's saying that if we have a polynomial and a fraction is a root, then the denominator has to divide the leading term and the numerator has to divide the constant term. This doesn't tell you anything about roots that are not rational. It just tells you if there is a rational root, then this has to be true. So here, let's note that the roots are x equals 1/2 and x equals minus 5/3, right? So we set this equal to 0, and that gives us x equals 1/2. Set this equals to 0, and that gives you x equals minus 5/3. If we multiply this out, right, I'll set up my little box because that's how I like to do these things. I get 6x squared minus 3x, 10x minus 5, and so my polynomial here is this, right? And so the leading term coefficient is 6, and this has factors 1, 2, 3, and 6. The constant term is minus 5, and that's got factors 1 and 5. And keep in mind that all of your factors could be positive or negative. So we'll just throw those there. Okay. So if we check our roots, the numerator, the 1 and the 5, those are those two numbers, and the denominator, the 2 and the 3, those are numbers in there. And you can see why that happens, right? The denominators are the things that are multiplied by x in your factor. So 2x times 3x, that gives me the 6, right? And so when we solve this for x, the 2 and the 3 ended up on the bottom. The 1 and the 5, when we solve those for x, they ended up on the top, and they multiply together to give you the constant term. So if we look at this one, can we find the leading term and the constant term without multiplying the whole thing? Well, the leading term is multiply all the terms that have x's in them together. So that's 2x times 3x times x times 13x. 13 times 3 is 39, and times 2 is 78. So this is 78x to the 4th. Shouldn't have that there. This is the leading term. If you multiply a bunch of factors, multiplying just the numbers will give you the constant term. So minus 1 times 5 times minus 11 times 2, right? And that's minus 55 times 2 is minus 110 times the minus 1 is 110. So there's the constant term. If you multiplied out the polynomial entirely, you get 78x to the fourth plus something, we can call a 3x cubed, plus something times x squared, plus something else times x to the first, plus 110. Right? And I'm not going to calculate out what these three numbers are because I'm only interested in these two. So what are my actual roots? Right? 2x minus 1 equals 0 gives me x equals 1/2. That's the root corresponding to this factor. 3x plus 5 equals 0 gives me x equals minus 5/3. That's the root corresponding to this factor. X minus 11 equals 0. That gives me x equals 11 as a root. That goes with that factor. And 13x plus 2 equals 0. That gives me x equals 2 over 13 with a minus sign as a factor. So these are my roots, right? If I look at the denominators, 2, 3, that's 11 over 1, and a 13, those are exactly the numbers that go into finding the 78. So 78 is divisible by 13. That's this number. 78 is divisible by 3 divided by 2. So the denominators are numbers that multiply together to give you the leading term. The numerators, the numbers in the top, the 1, the minus 5, the 11, and the minus 2, 1, 5, minus 11, 2, those are the numbers that multiply together to give you the constant term. So that makes things very useful here. We know that the leading term is 8x cubed, and we can list the factors of 8. And that's 1, 2, 4, and 8. And it could be either sign. Constant term, that's the minus 3. And the factors of minus 3 are plus or minus 1 or 3. So if a fraction is a solution to this equation, which fractions could it be? Well, and rational means fraction, it means division, rational roots. Could be, well, just take this, 1 over 1, so 1 over 1, 1 over 2, so that's 1 in the top and a 2 at bottom, a 1 over 4, or 1 over 8. Or you can take 3 as the top, and then you get 3 over 1, 3 over 2, 3 over 4, or 3 over 8, right? Because these are your possible tops, these are your possible bottoms, so 3 over 1, 3 over 2, 3 over 4, 3 over 8, and all of it can be plus or minuses. So here's a polynomial. What we know about this polynomial is that if a fraction is a root, it has to be one of these 16 fractions. And why 16? Well, there's 1, 2, 3, 4, 5, 6, 7, 8. Each one could be positive or negative. Sounds like a hassle checking all 16 of them, but on the other hand, there are infinitely many possible rational numbers, and so going from infinitely many numbers to check down to 16 is actually quite nice. So, long division. So we're going to leave this here for a moment. We know how to generate some roots. The immediate value theorem allows us to narrow down where our roots could be, right? You can have a root between 1 and 2. The rational root theorem tells us what possible fractions could be roots. So it cuts down our search for roots a lot. The question then is what do we do if we get a root? So we have long division. Graphing polynomials is hard because it's hard to find the roots, but polynomials can be split into factors through division. So this is the statement of sort of the theorem here. So if a function, the top function at the top, has a degree at least as big as the function at the bottom, then you can divide. You get a quotient plus a remainder over the denominator, or you can rewrite it if you multiply both sides by g of x, so that f of x equals this. Right? So if we take this thing and we multiply both sides by g of x, that gives us that part. And the degree of the remainder is strictly less than the degree of what you're dividing by. And this is really similar to the division of numbers. So we'll look at numbers first, because hopefully this is not completely unfamiliar to people. So I want to divide 138 by 7. So I write a 138 here, and I want to divide by 7, so put the 7 there. So how many times does 7 go into 13? It goes into 13 once. We put a 7 here, and we subtract. 13 minus 7 is 6. Bring down the 8. How many times does 7 go into 68? 7 goes into 68 9 times. 9 times 7 is 63, so we write a 63 there, and we subtract, we get 5. And 5 is less than 7, so we stop at this point. And we can write this in two different ways. We can say 138 over 7 is equal to 19 plus 5/7, right? There's our divisor, and there's a quotient and the remainder. This is our remainder. Or you can write it as 138 equals 19 times 7 plus 5, right? Just multiply both sides by 7. So two different ways to write it, but there's the output from log division. What about 138 divided by 6? Same process. 6 goes into 13 twice. That gives me 12. Subtract, you get minus 1. Pull down the 8, you get 18. 6 goes into 18 3 times. 6 times 3 is 18. So subtract, and you get 0. There's my remainder. And here we write it as 138 over 6 equals 23 plus 0 over 6, technically, because the remainder is 0, but we really don't keep that. Or we can say that we have factored 138. It's 23 plus 6. So factoring means that a remainder is 0, right? If we can factor something, then the remainder is 0. If you can't, if it's not a factor, right? 7 is not a factor of 138, the remainder is not 0. And the same thing happens for polynomials. So how do we divide this polynomial by that polynomial in long division? And it's pretty much the same thing as what we just did, except there's some details to keep in mind. One is that we need to have a column for every power. Right? So this has got no x squared term and no x term, but remember those mean that the coefficients are 0. And so we want to keep those in our statement here, because we want to keep everything nice and orderly, and we don't want to lose those terms. Same thing here. This is x squared plus 0x plus 5. So have a term for every possible power, right? 4, 3, 2, 1, and 0. Okay, how do we do this? Long division means you look at just the leading term of this and the leading term in here, and ask yourself, what do I multiply x squared by to get x to the 4th? Right? X squared times what equals x to the 4th? And the answer is, well, x squared. So we write down x squared there. Then I take the x squared and I multiply it by each one of these three terms, and that would give me an x to the 4th plus 0x cubed, right? X squared times 0x plus 5x squared. And then we subtract. X to the 4th minus x to the 4th is 0x to the 4th. 3x cubed minus 0x cubed is 3x cubed. 0x squared minus 5x squared is actually minus 5x squared. And so now you see why we need this column, even though there was no x squared term in there. Great. And then we bring down the 0x, and we bring down the plus 3. So there's the first step. So this is a 0x to the fourth, so we can ignore that because our highest term is gone. And now we've got a 3x cubed. So the question we ask ourselves now is we go back and we look at this x squared again and say, what do I multiply x squared by to get 3x cubed? Because that's the leading term of the polynomial in this line. And so that means we multiply by 3x, right? Because 3x times x squared gives me 3x cubed. So we put the 3x up here. And then the next line down here, we'll take this 3x and we'll multiply by each of these three terms. So 3x times x squared is a 3x cubed. 3x times 0x is a minus 0x squared, actually plus 0x squared. Actually, it doesn't matter because it's 0. And then 3x times 5 is a plus 15x. And we subtract. 3x cubed minus 3x cubed is 0x cubed. I'm not going to write that down because it's 0. Minus 5x squared minus 0x squared, that gives me minus 5x squared. 0 minus 15x is a minus 15x, and we bring down the 3. Great, so what do we do with this line? We're still thinking about this x squared, the leading term there, and we want to know what do we multiply x squared by to get this term? X squared times what is minus 5x squared? We multiply by minus 5. So we put the minus 5 up here. Now we take the minus 5 and multiply by each of these terms to get minus 5x squared minus 0x minus 25. And we subtract. Minus 5x squared minus minus 5x squared, that's 0x squared. So that's a 0. Minus 15 minus 0, that's a minus 15x. 3 minus minus 25 is a plus 28. Now the degree here equals 1, right? This thing that we're dividing by is x squared plus 5. So if I ask myself, what do I multiply x squared by to get minus 15x? I'm going to have to deal with 1 over x, and I don't want to do that. So at this point, we stop. When your remainder is degree less than the thing you're dividing by, stop. So we can write this in two ways, right? We can either say that x to the fourth plus 3x cubed plus 3 divided by x squared plus 5 equals that thing, x squared plus 3x minus 5, plus the remainder, which is this, minus 15x plus 28 over whatever we're dividing by. The other way to write it is just multiply everything through by x squared plus 5, and that gives me x to the fourth plus 3x cubed plus 3 equals x squared plus 3x minus 5 times x squared plus 5 plus the remainder, minus 15x plus 28. Okay, so that's an example. It's a little bit random, but we just want to show you the details there. What we're interested in is what happens when you divide a polynomial by a factor, right? And factors are things like x minus 5 and 2x plus 3. So we're most interested in division by factors. So here's the thing. We want to divide by a factor. So what do we get here? We've got 2x cubed plus 5x squared minus 37x minus 60. And we want to divide that by x minus 4. Okay, so doing long division means looking at this term and then the leading term of the polynomial and asking yourself, x times what equals 2x cubed? And here that means our what is equal to 2x squared, because 2x squared times x gives me that. So we'll put a 2x squared here, take the 2x squared, multiply by both those terms, you get 2x cubed minus 8x squared, because 2x squared minus 4. And we do our subtraction. So this is 0, right? 2x cubed minus 2x cubed. 5 minus 8 is actually 13x squared. Bring down the minus 37x. Bring down the minus 60. Okay, so now we've got a new leading term, that's our 13x squared, and we say, okay, x, our leading term here, times what equals 13x squared, and that means our what here is 13x. So put the 13x up here, multiply the 13x by both of these terms, that gives me a 13x squared, minus, now 13 times 4 is 2652x, and we subtract. 13x squared minus 13x squared is 0, minus 37 minus 52 is minus 37 plus 52, which is a 15x, and then we have a minus 60. So our leading term here is 15x, x times what, because this is our leading term here, equals, x times what equals 15x, and the answer is 15. So we'll throw in a 15 here. And then we take the 15 and we multiply by both those terms. We get 15x minus 60. We subtract. 15 minus 15 is 0. Minus 60 minus 60 is also 0. So we just get 0 as our remainder. And so a very nice thing happens here, right? And it's very similar to this, right? Where we got 138 actually has 6 as a factor. This polynomial has x minus 4 as a factor. So we can write our solution as 2x squared plus 13x plus 15 over x minus 4 equals, ignore that, 2x cubed, right? This is what we're dividing by, plus 5x squared, so 5, minus 37x minus 60 over x minus 4 equals 2x squared plus 13x plus 15 plus 0 over x minus 4. Or 2x cubed plus 5x squared minus 37x minus 60 equals x minus 4 times 2x squared plus 13x plus 15. We have actually factored something out, right? So we found out somehow that 4 is a root, x minus 4 is a factor, and now we can actually factor this entire expression, right? This entire polynomial, because we know x minus 4 is one factor, and this is a quadratic, and we know how to factor quadratics using the quadratic formula. Okay, so that's a bit of work, but we can do a much simpler version of it called synthetic division. And so here, x minus 4 is a factor, and that corresponds to x equals 4 as a possible root. And this is a possible factor. We don't know it's a factor yet because we actually have to do the division. So we'll take the 4, not the minus 4, but the 4, and we'll put it in a little box there. And we'll write 2, 2, 5, minus 37, minus 60. I'm going to say that this is my x cubed column, my x squared column, my x to the first column, and my constant column. And then I'll put a line down here. How does synthetic division work? Well, we start with this number, the 2, and we just bring it down. Then we take 2 times 4 is 8. So 2 times 4 is 8, and we add 8 plus 5 is 13. 4 times 13 is 52, and we add, and that gives me 15. 4 times 15 is 60, and we add, and we get 0. Now, when we're factoring something out, we're lowering the degree by 1. So this is actually now, after the division, my x squared column, my x to the first column, my constant column, and my remainder. So how to read this chart is to say that 2x cubed plus 5x squared minus 37x minus 60, that's this top row, is equal to 2x squared plus 13x plus 15 times our factor that we divided by x minus 4 plus the remainder. So it did our factorization, it did our division actually much cleaner. You can see that the numbers are actually the same though, right? Because we've got an 8, a 52, and a 60, right? And there's our 8, our 52, and our 60, right? That's these three numbers. And we had a 5 and an 8 added together, right? Our 5 plus 8 added together to give us a 13. And then we did 37 and a 52 added together to give us 15. So that's this column, and then adding the 60s. So synthetic division is a useful way to do division by a factor. It's a little quicker, and it gives you a, but it's doing the same thing as long division. So we'll do much more synthetic division than we will do long division. So this is the nice thing that we get when we do synthetic division by a factor, x minus c, you get something that looks like that. And we got that here, right? Our function is equal to the quotient, which is 2x squared plus 13x plus 15, times the factor x minus 4 plus the remainder. So we want to divide this thing by this. So we'll set up the synthetic division. We'll have an x to the 7th column, an x to the 6th, and x to the 5th. You have to have one column for each power, starting with the leading term and going down to the constant term. My coefficients are 1, minus 3. There's no x to the 5th term. There's no x to the 4th term. There's no x cubed term. There is an x squared term. There's no x to the 1st term. And there's a constant term. Here, the corresponding number that we want to use is minus 2, because that would be the root that goes with that factor, if this is actually a root. So we'll plug in a minus 2 there. After we do the division, we'll have an x to the 6th, an x to the 4th, an x to the 4th, x to the 6th, x to the 5th, x to the 4th, x to the cubed, x squared, x to the 1st, constant, and then a remainder column, right? Because when we divide, we're going to be lowering the degree by 1. So how does synthetic division go again? Take the 1, bring it down. 1 times minus 2 is minus 2, and add minus 3 plus minus 2 is minus 5. Minus 5 times minus 2 is 10, and add down, that gives me 10. 10 times minus 2 is minus 20. Add going down, that gives me minus 20. Minus 20 times minus 2 is 40. Add going down, and that gives me 40. 40 times minus 2 is minus 80. Add the 2, that gives me minus 78. Minus 78 times 2 is 156. Add going down, and that gives me 156. 156 times 2 is 312, minus 312. At least I hope it is. Yes, it is. Minus 312 plus 1 is minus 311. And that'll be my remainder. So what is the result that we get? X to the 7th minus 3x to the 6th plus 2x squared plus 1 equals this long polynomial, which is 1x to the 6th minus 5x to the 5th plus 10x to the 4th minus 20x cubed plus 40x squared minus 78x plus 156, which is a very long polynomial. And all that is times my x plus 2. And then we have minus 311 because that's a remainder. Great. So x plus 2 is not a factor, right? Didn't turn out to be a factor. That's okay, right? We would need to get a 0 here for it to be a factor, right? We need a remainder of 0. But we can't answer this question. What's p of minus 2? Well, p of minus 2 is what you get when you plug minus 2 into this and multiply it out and see what you get. But it's also, since these two formulas are equal, what we get when we plug in minus 2 into all of this times x plus 2 minus 311. And that's just a blob. So if I plug in x equals minus 2 into all of this, I get some kind of horrible, nasty thing here. But here, minus 2 plus 2 is equal to 0. This whole thing just goes away because it's some big, nasty number times 0. And so all we get is minus 311. Which is what we see here, right? If you plug in c for x, right, f of c, you get what? You get q of c times c minus c plus whatever your remainder was. But the remainder is going to have to be equal to, because this is equal to 0, the remainder is actually what you get when you plug the number c into the original function. So it also gives you a way to evaluate polynomials using synthetic division instead of, actually plugging a number into that, which would be much more useful if there was no such thing as calculators, but that's how that goes. So here's a polynomial. We want to be able to factor it, and then after that, we want to be able to graph it. So we have a table of values. And what does the IVT, which is the intermediate value theorem, tell us about this? So we look at the table of values. We know that this is an x-intercept, right? Because the y value is 0, right? And that's what an x-intercept is. But we also know that there's an x-intercept in here. Don't know what it is, but there's definitely an x-intercept between there because when x equals 1, the graph is above the x-axis. When x equals 2, the graph is below the x-axis. So we know one x-intercept, and we know where another one is. Maybe there are more x-intercepts. There could be up to 4, because could be up to 4 factors because it's a fifth degree polynomial. But from this table, all we're getting is that 7 is an x-intercept, and there's one between 1 and 2. So we can use synthetic division to factor out an x minus 7. So again, setting this up, we'll take x to the 4th column, an x cubed column, an x squared column, an x to the 1st column, and a constant column. And then we put in our coefficients: 2, minus 17, 25, minus 34, 42. And our x value is 7. And after we do the synthetic division, we'll have an x cubed, an x squared, an x to the 1st, and a constant, and then a remainder. And we're really hoping that the remainder is 0, right? Because that's what we see in our table. So we pull down the 2. 2 times 7 is 14. 14 plus minus 17 is minus 3. 7 times minus 3 is minus 21. 25 plus minus 21 is 4. 4 times 7 is 28. 28 plus minus 34 is minus 6. Minus 6 times 7 is minus 42. And hooray, 42 plus minus 42 is 0. We've got that 7 is a root, or x minus 7 is a factor. So this polynomial here, which is 2x to the 4th minus 17x cubed plus 25x squared minus 34x plus 42 is equal to this polynomial, 2x cubed minus 3x squared plus 4x minus 6 times that polynomial times the factor x minus 7 that we've now factored out. So now we have a cubic. What can we do with that? Well, we know that there is a root between 1 and 2. And so our polynomial, this one now, right? If there's another root to this polynomial, it's got to be one of the roots of this one. So that's 2x cubed minus 3x squared, 2x cubed minus 3x squared, and I think that was a plus 4x minus 6. And I think from the table up here, right, between 1 and 2 was where our root is. So the rational root theorem, we look at the factors of the constant. It'll be plus or minus 1, 2, 3, and 6, right? Because we're looking at factors of that. And we want factors of the coefficient in the leading term. And that's plus or minus 1 or 2, because that's that term. And we know that any possible rational root has to have one of these numbers in the top and one of these numbers in the bottom. So the possible rational roots are 1 over 1, 2 over 1, 3 over 1, 6 over 1, or 1 over 2, 2 over 2, 3 over 2, or 6 over 2. Plus or minus, right? So we take these numbers, we put them up in the top, and then, right, 1, 2, 3, 6, and we put 1s in the bottom and 2s in the bottom. This is equal to 1, 2, 3, 6. 2 over 2 is equal to 1, so that's repeated. 6 over 2 is equal to 3, so we don't need that. So actually we're getting 1, 2, 3, 4, 5, 6, 12 possible numbers. But we know it's somewhere between 1 and 2. And this is the only possibility. If a rational number is a root, it's got to be 3 halves, because that's the only one that's between 1 and 2. So we want to see if we can get this root out of there. So 3 halves is my root that I'm looking for. My x cubed, x squared, x to the first constant, 2 minus 3, 4 minus 6. And then we'll do the division, and down at the bottom, I've got an x squared, an x to the first, a constant, and a remainder. And again, I'm hoping that my remainder turns out to be 0, because I want this to be a root. So 2 goes to, bring it down to 2. 2 times 3 halves, this is a plus 3 halves. 2 times 3 halves is 3. 3 plus minus 3 is 0. 0 times 3 halves is 0. 4 plus 0 is 4. 4 times 3 halves is the same thing as 12 divided by 2, which is plus 6. Add that together, we get 0. So yes, we're very happy about that. So what do we know then is that 2x cubed minus 3x squared plus 4x minus 6 equals 2x squared plus 4 times, well, it's times the factor that has that as a root, which is x minus 3 halves. And I can tidy that up a little bit. Two x squared plus 4 times x minus 3 halves. I can factor a 2 out of this, so that's going to be x squared plus 4 times 2 times x minus 3/2. And I can multiply now that distribute this 2 into the other factor. Oh, sorry, x squared plus 2, because I factored out the 2, times 2x minus 3. So what do we actually have here now? Our original polynomial, way up at the top, is this one. Um, yep. So original polynomial is 2x to the 4th minus 17x cubed plus 25x squared minus 34x plus 42. We showed that you could factor out an x minus 7. And when we factored out an x minus 7, we got this polynomial. And then we showed we could factor out of that polynomial a 2x minus 3. And then what's left after that is an x squared plus 2. Can we factor x squared plus 2? And yes, we can do that, because we know how to factor quadratics. You set the equal to 0 and you solve for x. You can use a quadratic formula. You can do a number of different things to solve that. But if we set this equal to 0 and solve for x, that'll give us the roots. And once we have the roots, we can figure out the factors. So this is actually not too hard to solve. It's x squared equals minus 2, which means x equals plus or minus square root of minus 2. And we know how to handle those. That's plus or minus I because of the minus sign times square root of 2. So our two roots are x equals I root 2 and x equals minus I root 2, which means the corresponding factors are x minus I square root of 2 and x plus I square root of 2. And note that a rational root theorem doesn't pick up these two roots because they're not rational. If you don't have rational roots, right, either complex ones or square root of 2, square root of 3, square root of 17, whatever, the rational root theorem won't pick those up, which can be a little annoying. So finally, our polynomial 2x to the 4th minus 17x cubed plus 25x squared minus 34x plus 42 can be written as x minus 7 times 2x minus 3 times x minus I square root of 2 times x plus I square root of 2. And there it is, fully factored. There's only two x-intercepts. One is x equals 7, and one is x equals 3/2. They both have odd multiplicities. That means that the graph goes through the x-axis at those two x-intercepts, because we did want to graph this thing. We also know that the leading term is even degree, and it's a positive coefficient. Now we can sketch something like a graph. And again, our graphs are really just paying attention to where the graph is above or below the x-axis. So here's my x-axis, here's my y-axis. End behavior is like this because it's even with a positive coefficient. At x equals 7 and at x equals 3/2, the graph goes through the x-axis. And so the graph will look something like that. There might be some tweaks in it, right? We don't know exactly what those details are, but we do know that from minus infinity all the way up to 3/2, the graph is positive. From 3/2 to 7, the graph is negative, and then from 7 all the way out to infinity, the graph is positive. And so with the aid of the rational root theorem and the intermediate value theorem and just starting with a giant list of a table of numbers and then using synthetic division, we're actually able to factor this polynomial. And the idea is that we should be able to break down a polynomial in this form into a product of factors with various multiplicities. So there's two different ways to write polynomials, either like in a fully factored form, which is sort of what we want so we can graph it, or in a multiplied out form. And the multiplied out form is useful for other things, especially when you get into calculus. If you're going to differentiate or integrate that function, having it multiplied out is much more convenient than having it factored. So here's some highlights about it. And apparently I forgot to change the text size consistently, but that's okay. And that will be it on factoring.